So the next application is the so-called critical path problem. It is, in a sense, the opposite of the shortest path problem. I want to find the path of greatest length, the longest path in a digraph. That's also another change. But why ever would I want to find the longest path? Surely that has no practical applications. Well, it does. And you have all done this at least once. So imagine you're cooking and you start by chopping onions. Some of these onions you want to put in a salad. Some of these onions you want to fry. And then after frying, you want to cook something else. And then you put everything together with the salad and you get your meal. So how long time does this take? Well, assuming that this frying and something else takes longer time, this is what's important. This is what is critical. This is the bottleneck. So if you want to calculate how long time this meal will take, you have to take into account the chopping onions plus the frying part. Making the salad doesn't take so much time, so that's not the critical thing. So in other words, if you have an activity network, which means that you have sort of a network made of certain activities that need to be done in a certain order. For example, you need to chop the onion before making the salad and before frying and so on. Then you want to calculate which sequence of events will take the longest time. And this is the sequence that you would need to start first in that case, which is, I'm sure, how you reason when you cook, perhaps without using weighted digraphs. But weighted digraphs is the way to solve these problems in general. And the solution consists of a version of Dijkstra's algorithm modified so that it works for this problem. So how does this algorithm work? Let's take a look. So we're going to apply the general algorithm to this particular graph to illustrate how it works. Again, you want to go from A to B, but now the graph is directed, so you have to respect the directions. And again, what you want now is the longest, not the shortest path. So you start with A and give it the value 0, as before. Now you set values to the adjacent vertices. Of course, you have to respect the directions. So this vertex gets value 1, 0 plus 1. 0 plus 2 gives you 2, and 0 plus 2 gives you 2 here. Okay. Now you go through not just the shortest one, but also not just the longest one, because you don't know what will happen later. So you have to go through all these vertices and change or attribute values to whatever is adjacent to them. And you change the values whenever they increase now, not decrease. Let's see how it works. So from this edge with value, from this vertex with value 1, I know that there is no other way to reach this vertex because the only arc leading into this vertex is this one. So this one has to have the value 1. From this vertex, I can reach this vertex that previously got the value 2, but now look, I have a longer path. 1 plus 3 is 4. So I change the value. The longest path to this vertex has length 4, not 2. And I'm looking for the longest path overall, so I want to inflate these numbers as much as I can. For B, I have 1 plus 4, that is 5. Then I go to this vertex. This vertex has no other edges leading into them, no other arcs leading into them, so that's my only possibility. From this vertex, I can go to B. And now if I do that, I get 2 plus 7, which is 9, which is longer than 5. So that's what I want to record as my longest path. Very good. Then I go to the next vertex, which is this one with 4. The only paths that led to this vertex I've already examined, and the longest one had length 4. From this vertex, I can only go to B, and I can do that by adding 9, and 4 plus 9 is 13, which is longer, so I get 13. And then I am done, because now I have gone through all possible vertices, and the longest possible path to reach B has length 13. So again, in this algorithm, the difference is that you have to go through all vertices and you adjust when the values increase, not decrease. But the way to find an actual path of the longest length is the same as with Dijkstra. So you start with this one, which has value 13, and you check where is the value, the weight of the edge, equal to the difference between the values of the edges. So if B has value 13, this has value or weight 7, comes from a vertex of value 2, but 2 plus 7 is not 13, so I could not possibly have got 13 going this way, neither this way, because 4 is not the difference between 13 and 1. It has to be this way, because 9 is equal to 13 minus 4. Same here, this 4 doesn't come from 0 by an addition of 2. It has to come from 1 by an addition of 3. And the last step is clear. So this is the path of longest length. These 3 steps of my recipe or road building or whatever project I'm doing, these 3 steps will be the ones that will define the length of how much this operation is going to take. And this is good to know because, for example, suppose you have some delay in this part. Then that's not so important because even if you have a short delay, it will not affect the length of this longest path. But if you have a delay in one of the steps of the longest path, then the whole operation will take more time. So this is the reason why you sometimes want to calculate the longest path. And as I just mentioned, to find the critical path, you trace back as in with the shortest path problem.